Okay, so in this video I'm going to take a look here at the normal distribution. This is a fairly classic distribution. It's probably the one that we rely on most in statistics and data science and in economics. The graphs here that I'm going to use come from a statistics textbook that I used a few years ago and found it quite useful. So the authors are Burson, Levine, and Crivel, and I found the slides were quite good, and I found the solutions, but also in particular, lots of the estimations were set up in Excel. At the time, very few books used Excel, so I'm gonna use Excel here as well. Starting point might be you would take a look at the cumulative standardized normal distribution. This, if you like, is a way of capturing or a way of representing, the probability that particular events could occur. And often the starting point is here we say we take a kind of contrived situation where we say the mean of a population is 0. Mean is 0. And then the standard deviation of the population is 1. And then within typically two standard deviations, negative 1.96 and positive 1.96 standard deviations, you typically get 95% of the population. Okay, so this distribution is heavily used in finance. In particular, we see it used in Black-Scholes model. We see it used in valued risk models. A lot of the logic that is used to develop these type of risk modeling type scenarios very often come back, and the insights that are developed, the intuition behind those models, risk models, very often rest with this idea that if we have a population, then typically most of the observations center around the mean, and then the more extreme values in the population tend to be far and few between. So if we go out the extreme tails, right, we tend to observe those outcomes much more rarely. And then also in this Gaussian normal distribution, we take it as given that the area under the curve, right, and the curve here, the density function or the mass function, is given by this mathematical expression that the area under the curve is equal to 1 or 100%. And so, for instance, if we had this contrived example where we said, what's the area under the curve, where we have 0.12, so we have a standard deviate, so positive 0.12 standard deviations away from the mean, then the area under the curve, if we read the tables here, come down to 0.1, go across to 0.02, and we read 5478. Now I'll take an actual set of tables and take a look at that. Okay, so I have here normal cumulative probability distribution, Gaussian distribution, and again we're looking, they're kind of what we would see in an actual exam. Right, and let's just bring it into, take these values for a second. So we're reading, if we go back into where we started, we're reading what's the area under the curve going 0.12 standard deviations away from the mean. If it was from 0, then the area under the curve would be 0.5. Right, so we can demonstrate. I'll go back in here to these actual tables that I have. If we take the area under the curve going from 0 back, 0.5. If I want to read 0.12, I come down here, 0.12, and I come across to 2. And it's 5478, and it's assumed we know that in front of the 5478 there's a decimal place, so it's 05478. Okay, let's take a look in on our page here. 0.5478, so it's the same result. Okay, so let's go into Excel again for a moment here, and we start this afresh. And if I was to do that in Excel, read the area under the curve, I would invoke equal to norms dist. Just very simply, norms dist, open bracket, 0.12, close brackets. And that should give me here the 0.5478. Where is 8? Well, it's just because of the rounding. Right, 0.5478. So if I set out, if we put a value of 0 here and said what's the area under the curve, to read the probability in Excel, we invoke norms dist. Right, and norms dist assumes that the mean is 0 and the standard deviation is 1. Okay, and then we return that and we have 0.5. Okay, so that's what we would expect from the tables, right? 0. Reading the area under the curve, going back, we get 0.5. Okay, now most of the time, however, we find that the numbers we're working with don't necessarily conform to a standardized normal distribution. So when we get actual numbers, real world numbers, we have to standardize, and that means convert them into a z-score. So if, for instance, we had started with a situation where we were told that the mean of the population was 5 and the standard deviation was 10, so that differs from what we have up here, mean of 0, standard deviation of 1. But if you start with a mean of 5, standard deviation of 10, and then we want to know approximately what was the probability of getting an outcome or finding a variable that had a value less than 6.2, then we take that 6.2, we subtract away the mean, and we divide by the standard deviation of 10, and then that would yield 0.12, and we would read it in the same way. So for instance, in this particular specification, if we were to set that up in Excel, we would have something like this. We have a mean of 5. We want to find the area under the curve going back from 6.2, I think, and the standard deviation was 10. Okay, so that looks about, let me just check that. Let's go back. Okay, so we have mean of 5, 6.2, 10. Mean of 5, 6.2, and 10. Okay, and we have that z-score. Okay, so a couple of things then worth noting. The first one is, to get the probability here, we could use norm dist, right? So as before, if I use norms dist, I can read directly norms dist, and the area under the curve, as before, is that 5478. So when we round it, we got 778, right? So just round it back, and 5478. Okay. But if we didn't convert to z-score, we could have used the other function, not norms dist, but actually, because that is explicitly here indicating you read a z-score. Right, we can read directly from here. So by that I mean we can use another function in Excel called norm dist. So equal to norm, and then no s, just dist, open brackets. And then we specify, well, we want to find the area, the probability of getting a variable less than 6.2, 6.2 or less, where we know the mean is 5, and again following line here, where the standard deviation is 10, and Is it a cumulative normal probability? Yes, it is, so we put in true. And we get the same value. Okay, so we get that 5, 4, 7, 8 again. Again, this is for where we use norms, and this is where we use norm. DIST. DIST. Okay, so again, if we go back into our distribution here for a moment, right? The area under the curve, so this is exaggerated. The areas here that are shaded in are exaggerated, but the area under the curve here is 5478, 0.5478. Also of interest here is perhaps how do we recreate the distribution here? And again, you may have noted that there was two options, right? There was also the option when I put in norm dist, so equal to norm dist, right? There was two options. One was, okay, cumulative. The other was the probability density. So for instance, in this case, I can run the same estimation. So what's the probability of getting a value less than 6.2, where the mean is equal to 5, the standard deviation is equal to 10, and yes, we're looking for a probability true. Okay, we get a probability output. But if I change the final specification here, the final argument to being false, then notice we get the probability mass function. Okay, and we get this value 0.0396. Now, where am I getting that from? Well, we come back here again and just click on norms dist and go into the function for a moment. And what you find is that's been this density, normal density function, right, is obtained by using this expression here, where I have 1 over 2 pi sigma e to the power of mu x minus mu 2 the variance, 2 times the variance, 2 standard deviation squared, squaring on top, close out the brackets, keeping in mind the exponential has a negative power here. Again, in the expression we had before, right, we had written it here, and that's the same expression. In fact, it looks slightly different. It's actually the same. We have a negative here also, and we have squares, 2 sigma squares, so on. So this is the same, right? Okay, so in the next video, I'm going to go back into Excel and look at this a little bit more, set it up in a little bit more rigorous fashion, and just replicate the values that I'm getting and explain a little bit more thoroughly the density function, the estimating the probability, and then also then introduce R here as well for understanding some of the basic concepts.